Unit 3, Rational Functions, Notes, Day 1. Recall that a rational function is a function whose rule is the quotient of two polynomials. So it's a polynomial divided by a polynomial. And here we have some examples. So we're going to find the domain of our rational function. So remember, domain is a set of all real numbers except for x values that make the denominator 0. So in order to find, it's helpful to factor the denominator and focus on what's happening there. So for this, remember, when we find the domain of a function, we said we had the two rules for our domain restrictions. The first one was variables in the denominator, which rational functions have variables in their denominators. And also, it's when we have variables underneath an even roots. So rational functions don't have radicals in them, so that's going to make this a lot easier. So if I look at this first example, what makes my denominator equal to 0? I know that 0 makes x equal 0. So in this case, that means that the domain is going to be all real numbers except for 0. So negative infinity to 0 and 0 to infinity. Looking at number 2, if I want to figure out where the denominator is equal to 0, I need a factor, or I could use a quadratic formula. So in this case, we have x minus 3 times x plus 2. And if we set both those equal to 0 and solve, we would get x is equal to 3 here, and x is equal to negative 2. So my domain is going to be all real numbers except for 3 and negative 2. So the domain is negative infinity to negative 2, negative 2 to 3, and 3 to infinity. Looking at C here, same thing, we set the denominator equal to 0 and solve. So when I solve, I have x squared minus 3 equals 0. So x squared is equal to 3. And then, of course, when we take away even power, don't forget to do plus or minus the square root. So plus or minus root 3. So our domain would be all real numbers except for negative root 3 and positive root 3. So negative infinity to negative root 3. Negative root 3 to positive root 3, and positive root 3 to infinity. The next thing we're going to talk about is our intercepts. So for our y-intercepts, remember that in order to find it, you're plugging 0 in for x and solving. For the x-intercept, you plug 0 in for y and solve. Note that not all rational functions have x and y intercepts, so just kind of keep that in mind because we will be graphing these functions without using our graphing calculator, so that's helpful to know. So looking at our first question, it says to find the x and y intercepts and the domain of this function. So in order to do that, if we want to find the y-intercept, we know that we're plugging 0 in for x. So that would give us 0 squared minus 0 minus 2 over 0 minus 1, which is equal to negative 2 over negative 1, so 2. So that means our y-intercept in this case would be 0, 2. For the x-intercept, that's when we set the equation equal to 0 and solve. So we have 0 is equal to x squared minus x minus 2 over x minus 1. But we don't like having that in our denominator, so if I were to multiply both sides by x minus 1 to get it out of the denominator, notice that we would have x minus 1 times 0, which is just 0. So a lot of the times when you're solving for a rational function, really it's just the zeros in the numerators, but you also have to check to make sure that they're not zeros in the denominator because we can't divide by 0. So if they would be a 0 of the denominator and the numerator, then you know it's not an x-intercept. So in order to go ahead and solve this, we can go ahead and factor. So we get 0 is equal to x minus 2 times x plus 1. So then our zeros are x minus 2 and 0 equals x plus 1. So of course we get x is equal to 2 and x is equal to negative 1. So those are my x-intercepts then. So for my x-intercepts I have 2, 0, and negative 1, 0. Then for the next part, we're taking a look at the domain of the function. So remember the domain goes along with the zeros of our denominator. And so in this case, what makes my denominator equal to 0? X is equal to positive 1. So that means my domain is going to be negative infinity to 1 and 1 to infinity. And so a lot of that we've done before. We're just kind of revisiting it to help us graph these. For our vertical asymptotes are going to be zeros at the denominator that are not zeros at the numerator. Remember that your graph approaches your vertical asymptotes but never crosses or touches because we know the function is not defined at that value of x because you can't have 0 in your denominator. So we're going to be graphing these, and it's helpful when you're graphing these to talk about what's called the big little concept, which helps us look at what's happening at our vertical asymptotes. So the big little concept, it says if c is a number far from 0, then 1 over c is a number close to 0. And if c is close to 0, then 1 over c is far from 0. So what does that mean? So that means that if you have 1 over a very large number, it's equal to a little number, and 1 over a very little number is equal to a big number, which helps us when we're actually graphing these, which you'll see in the next problem. So just real quickly, if we look at this, so we have 1 over negative 1,000, which we know is equal to negative 0.001. So 1 over a very large negative number is a very small negative number. And so in this case, same thing. So I have 1 over, and we just said that this whole fraction in my denominator is negative 0.001. So 1 over a very small number is a big number. Because remember, when you divide by a fraction, you multiply by the reciprocal of what's in your denominator. So this would be negative 1,000 over 1 times 1 is just equal to negative 1,000. And as you can see, so 1 over a very small negative number is a very large negative number. So that's the big little concept. So let's go ahead and use that to help us graph this next problem. So we want to sketch a graph of this, and then we're also going to talk about the domain and intercepts. So let's go ahead and start off with what we know. We can go ahead and factor this. That's usually the first thing that I do. So I have x plus 1 over 2 times x minus 2. And if I am graphing this, I'm going to want to find my x and y intercepts. So for my y-intercept, we know we're going to set 0 in for x and solve. So we get 0 plus 1 over 2 times 0 minus 2. So that, of course, that's going to give us 1 over 2 times negative 2, which is negative 1/4. So that gives me my y-intercept is 0, negative 1/4. And for my x-intercepts, we set the equation equal to 0 and solve. So remember, we said it's really just the zeros of the numerator as long as they're not zeros in the denominator, which in this case we don't have common zeros in my numerator and denominator. So 0 equals x plus 1. So when we solve, we get x is equal to negative 1. So my x-intercept is negative 1, 0. My domain is, of course, zeros of the denominator. So if I set this equal to 0 and solve, I get x is equal to 2. So my domain is going to be negative infinity to 2 to infinity. So let's go ahead and think about graphing this. So in my denominator, I know that I cannot have 2. And so that means I have a vertical asymptote at an x value of 2. And then for our horizontal asymptotes, we did talk about this last year. So if you recall from last year, when the numerator degree is equal to the denominator degree, we know that there is a horizontal asymptote at whatever the leading coefficients are. So in this case, the leading coefficient of my numerator is 1, and in my denominator is 2. So I actually have a horizontal asymptote at y equals, in this case, 1/2. Which would be right here. And of course, we said that my vertical asymptote was at x equals 2 because it's the zeros of your denominator. So if I'm graphing this, I would use my y-intercept to help me and my x-intercept. So we have a y-intercept is 0, negative 1/4, which would be somewhere in here, and an x-intercept of negative 1, 0. So remember that your graph follows along your asymptotes, and we'll talk more about the horizontal asymptote in the next day. So remember that your graph is following your horizontal asymptotes because that's the end behavior as you get very large values of x in the negative direction. And over here, we know that our graph doesn't cross the x-axis again because we only had that one x-intercept, and so our graph is just going to continue and follow along our vertical asymptote without touching or crossing over it because, again, we can't get 0 in the denominator. So we can actually use the big little concept to help us figure out where our graph is going on the left and the right side of our vertical asymptote. So the way that we read this, we would say, so we know that this is the left side of the asymptote and this is the right. And so if we're thinking about the left side and the right side, to the left of 2, what are numbers that are close to that but not equal to? Well, I know that 1.9 is close to 2 but not equal to. And then I can get even closer if I did 1.99, 1.999, and if I keep adding 9s, it's going to get closer and closer to that value of 2. So what's happening as we're getting closer? So let's actually use the big little concept first. So if I were to plug 1.9 into my equation, I have, and I'm going to plug it into my factored form. So we have x plus 1 over 2 times x minus 2. So if I plug in 1.9, I get 1.9 plus 1 over 2 times 1.9 minus 2. So 1.9 plus 1 is 2.9 over, and then 1.9 minus 2 would be 2 times negative 0.1, which gives us 2.9 over negative 0.2. So this is what we were talking about. We have basically 1 over a very small number, because this 2.9 is not very large. So if I have something over a very small number, I know it's going to be equal to a very large number. Could we actually figure out what that is? If you wanted to use your calculator, of course you could. So if we were to actually plug in 1.9 and do this arithmetic here, we get negative 14.5. But I'm really just looking at the signs when I'm looking at this. So I would notice that the sign here is a positive divided by a negative. So that tells me this is going to go to negative infinity. So we can use our graphing calculator to kind of even check. So let's see what happens if we get even closer to 2, but not actually equal to 2 in our calculator. So I'm going to go ahead and plug this into my y equals. So don't forget, if you do plug it in, make sure you use parentheses around your numerator and denominator, because we're dividing everything. And then I'm going to change my table sets to ask, so we can ask what we want to get in our table. So 1.9 we just said was negative 14.5. 1.99 is even closer, so that, and if you notice, gives us negative 149.5. So if we did 1.99, oops, 9 and 1.9999. So as you can see, the closer and closer we're getting to 2, my values are becoming a larger and larger negative value. So this is negative 1,500 and negative 1,500, or sorry, 15,001. And so that confirms what our graph looks like as we're going down towards negative infinity. So we actually are going to start getting into some calculus writing of this. So the way that you can write this out, you would say, as x approaches, and in this case we're approaching an x value of 2. So as x approaches 2, we said that our y values are decreasing, so they're going towards negative infinity, which means they're decreasing without bound. Without bound just means it keeps going on forever, which is why it's negative infinity. So then the question is, what happens as x is approaching 2 from the right? So to denote the difference between the right and the left, so as x approaches 2, we use a negative sign up here to denote the left side, and if I wanted to denote the right side, I would say as x approaches 2 from the right. Now we want to figure out what's happening to the right side. So values that are to the right, if we go back up here, of 2, so we use 1.9 to the left, but values bigger than 2 would be values like 2.1, and if you look at the table, 2.01, 2.001, and 2.0001 gets even closer. So let's go ahead and look at the big little concept with now using 2.1. So if I plug that into my equation that we had before, which again was x plus 1 over 2 times x minus 2, so 2.1 plus 1 over 2 times 2.1 minus 2. So this gives us 3.1 over 2.1 minus 2, now you'll notice is 0.1. So we have 2 times 0.1, which is 3.1 over 0.2. So now you'll notice we have a positive divided by a positive. So we have a number over a very small number because, again, we're going to get smaller and smaller values as we get closer and closer to 2 from the right side. So that tells me this is going to be going towards positive infinity. So we can check our calculator table just to kind of make sure what we're saying is correct. So let's go ahead and do that. So if I go into my calculator, I'm going to just delete these values out because now we're going to use 2.1 and 2.01 and 2.001 and 2.0001. So as you see, the closer and closer we get to from the right, we're approaching a very large positive value. So now we're going up to positive infinity instead. So on here we have 15.5, 150.5, 1500.5, and 15,001. So as x approaches 2 from the right, f of x, or our y values, are going to infinity, which means the function is increasing without bound. So again, it's just going to keep going on and on and on to infinity. So if we go back up to our graph, that tells me that I'm in this upper portion of my graph. And so for that upper portion, I know that I'm not crossing my x-axis again, and I know that my graph follows along my asymptotes, so my graph would be up here. And we're going to talk more about graphing these functions later, but just even so you can see if I hit the graph on my calculator, you can see that here's what our graph looks like, which is similar to our graph. We're just drawing a rough sketch of it, and we'll talk more about graphing later. But it is important that you do understand the idea of this big little concept and looking at the left side and the right side of our graphs and what's happening. So let's go ahead and look at examples of vertical asymptotes at just some x value we're calling c. So c would be some number, such as in the last one, our x value was approaching 2. But again, we're just doing this in general. So we're saying x equals c for each of these. And so I can go ahead and write the notation. So for this first one, again, remember this is the left and this is the right side of c. So the notation is as x approaches c, and we use the plus sign to stand from the right. So if we're doing this side over here, what are my y values doing? So you can see your y values are going up towards infinity. So then we would say f of x approaches positive infinity. And as x approaches c from the left side, which we use the minus, again, you can see your y values are, as we're approaching this asymptote, are going up to infinity. So f of x approaches infinity. So whenever your left and the right side is going to the same place, which in this case was positive infinity, you can write it together. So we'll do that in the next one, because this next one you can see they're both going towards negative infinity as we approach c from the left and right. So a way that you can write that together would be as x approaches c from the right and left side, f of x approaches, in this case, negative infinity. So you can write that all together. That's okay. But as in the case of the next one, when you are going to separate places, such as this one's going to infinity and negative infinity on this side, so this goes to infinity, and this one's going towards negative infinity, you do have to write them separate. So as x approaches c from, let's do the left side first. So the left side, f of x, is approaching infinity, and as x approaches c from the right side, f of x now is approaching negative infinity. And that would be it for our notation. All right, so now we're going to look at holes and removable points of discontinuity. So it means the same thing. So if you say a removable point of discontinuity, it just means we're looking at our holes of our graph. So let's say we have a rational function, f of x, and g of x and h of x are being divided. And so we're going to say d is a 0 of the function. If the numerator and denominator has the same 0, and the multiplicity of the 0 in the numerator is greater than or equal to the 1 in the denominator, then there's a hole at that place. So in this case, x equals d. Otherwise, there's a vertical asymptote at x equals d. So what does that mean? Let's do some examples to kind of help out. Remember, the multiplicity is how many times the 0 occurs as a factor. So if we look at this first example, we have x minus 3 over x minus 3. Both factors only occur once in the numerator and denominator, which means they both only have multiplicity of 1. So if we were to simplify this, both the x minus 3's would cancel out to leave us with 1. However, if you look at your original function, we know that we have some domain restrictions. We can't have 0 in our denominator. So if we solve x minus 3 equals 0, we get x is equal to 3. So we know that our domain is negative infinity to 3 and 3 to infinity. So if I were to graph this, I know my graph is going to, both these graphs look similar. So if we have f of x equals 1, that's just a horizontal line at 1. But I can't draw just a horizontal line at 1 like this on my graph because we said before that we can't have 3 in our denominator. So that means whenever it cancels out of our denominator completely, we actually have a hole in our graph. So even if you were to look at your graphing calculator, so it doesn't show us there's a hole there, but if I do second trace value and I plug in an x value of 3, notice that nothing comes up for our y. And if I go to my table, so I'm going to change my table set back to auto and do second graph, you can see that there's an error at an x value of 3. So that's when we actually put an open circle to denote that hole in the graph. So that is what our graph would look like. And again, this is a hole. And so we actually want to figure out where that hole is at. And so to do that, you always use your simplified answer. So if I plug an x value of 3 in, then I get a y value of 1 because it's just a horizontal line. So that means I have a hole at 3, comma 1. So let's look at the next scenario. The next scenario, you'll notice that you have a multiplicity of 2 in the numerator and 1 in denominator, which means we have two factors of the same thing in our numerator and just the 1 in denominator. If I simplify this, notice that the x minus 3, one of them cancels out from the numerator and denominator, so we're left with x minus 3 to be simplified. So our domain, however, did not change because we still can't have 3 in the denominator, so our domain is still negative infinity to 3 and 3 to infinity. And if I plug 3 into my simplified answer, so now if I do 3 here, notice that I would get 3 minus 3, which is 0, but it's not a 0 in my denominator, it's a 0 in my numerator, which is okay. So this tells me, again, I have a hole at 3, comma 0. So if I were to graph this function here, I know it's a linear function, so I have a y-intercept of negative 3. My slope is going up 1 over 1. And at 3, 0, I would have an open circle. So if we just connect these, this is what my graph would look like. But again, because of the fact that we have that common 0 between our numerator and denominator, it cancels completely out of my denominator, and so it no longer makes my denominator 0 when I simplify it. Therefore, that's why that is a hole. And we can look at this in our calculator. So if I go to my y equals, I'm just going to insert a square here. And so if I look at my graph, you can see it looks like a straight line, so it's linear. And if I do second trace value 3, notice nothing comes up. And you can even look at your table and nothing comes up there either because of that hole, and because in the original equation it makes your denominator 0. So the next scenario that we have is what happens when the multiplicity of the denominator is greater. So now if we simplify this, notice that this cancels out and this cancels out, but we're still left with 1 in our denominator, so 1 over x minus 3. My domain, because of this, is still going to be negative infinity to 3 and 3 to infinity. And now if I plug my hole, or my domain restriction into my simplified answer here, notice I would get, so f of 3 would be equal to 1 over 3 minus 3, which is 1 over 0. I can't have 0 in my denominator, which means that this is not a hole, but instead this is a vertical asymptote at x equals 3 on my graph. So it's no longer a whole. If it's still left in your denominator when you simplify it, and it still makes your denominator 0 when you plug that number in, that is going to be, again, a vertical asymptote. So we have vertical asymptote here at 3. If we look at the numerator degree versus denominator degree, you can see the numerator degree is less than the denominator degree, which means we also have a horizontal asymptote at y equals 0, which again we'll talk about tomorrow. And this was x equals 3. So for this, then I could again use my big little concept to help me graph. So I have x equals 3 here. So something to the left of 3 would be 2.9. So if I use my big little concept to figure out where my graph is going to go, I can use that to help me. So if I'm going to use 2.9 and think about plugging it into my simplified answer because it's a lot easier than using the original one. So when I plug that in, I would get 1 over 2.9 minus 3, which is 1 over negative 0.1. So 1 over a very small negative number means that as x approaches 3 from the left side, our y values, or f of x, are going to be going towards negative infinity. So that tells me I'm in the lower region of my graph. And again, we're just drawing a sketch of the graph. So it'd be something like this, and I could also find my y-intercept if I wanted to. To find the y-intercept, I plug 0 in for x, so we get negative 1/3, so that's about right. So let's go ahead and look at the right side of 3. So the right side of 3 would be a number such as 3.1. So if I plug 3.1 into that equation, I get 1 over 3.1 minus 3, which is equal to 1 over 0.1. And again, now I have a positive divided by a positive number. So in this case, as x approaches 3 from the right side, your y values, or f of x, is now approaching positive infinity. And so on this part of my graph, it would go something like this, because you always follow your asymptotes. And again, we'll talk more about the graphing later, but that's just an idea of the big little concept again. So let's go ahead and look at the next equation. So for the next equation, again, we want to figure out our vertical asymptotes and or points of discontinuity, which are the holes. In order to do so, I want to factor. So I have to factor my numerator, which is the difference of cubes, or 2 cubes, I should say. So that factors into a binomial times a trinomial. So the sign is minus, so same sign, opposite, always positive. First term is going to be x, the second term is 2, which is whatever the cube root of those numbers are. The first term squared is x squared, first term times second term, so 2x, and second term squared is 4. My denominator is already factored, which makes it a little bit easier. And so notice that the x minus 2 from your numerator and denominator cancel out. So in my numerator, I'm left with x squared plus 2x plus 4. And in my denominator, just have x plus 2. So we have to go back. What made my denominator from my original equation 0? So if I set both these equal to 0 and solve, I would get x is equal to 2 for this first one, because 2 minus 2 is 0, and x equals negative 2 for this next one, because negative 2 plus 2 is 0. So that means my domain is negative infinity to 2, negative 2, excuse me, and then negative 2 to positive 2, and 2 to infinity. Sorry, my pen's not writing real well right now. So now I need to look at 2 and negative 2 to figure out if it's a vertical asymptote or a hole. So if we were to plug into this equation positive 2, so if I plug 2 in here, I would get 2 squared, which is 4, plus 2 times 2 is 4, plus 4. In my denominator, if I plug 2 in here, I would get 2 plus 2. And notice it did not make my denominator 0. Because it did not make my denominator 0 means this is a hole. And so where is that hole? We just have to figure out our value. So 4 plus 4 plus 4 is 12, and 2 plus 2 is 4 in my denominator. So 12 divided by 4 is 3, so that means I have a hole at 2 comma 3. And again, we just use our simplified answer, which was this right here, to figure out if it's a hole versus vertical asymptote. So again, because when I plugged that 2 that originally made my denominator 0, and I got a number out, that's where my hole is at. So now if I plug in instead -2 into my equation, notice that if I plug -2 in right here for x, -2 plus 2 is equal to 0, which makes my denominator 0, and I can't have 0 in my denominator, so therefore I know that -2 is a vertical asymptote. And don't forget to write x equals -2 because a vertical asymptote is a vertical line. And that's it for my holes and vertical asymptotes there. So now I take a minute to see if you can pause the video and to see if you can figure out any vertical asymptotes or removable points of discontinuity / holes for the equations below. And then unpause it when you're done so we can look at it. So if I look at this first one, notice that when I simplify it, this becomes 1 over x plus 3. So the areas that I'm concerned with, what makes my denominator equal to 0, so x equals, and in this case, because it was x minus 2, I know x equals 2, and what makes this 0, -3. So those are my areas of concern. So when I plug 2 into my simplified answer here, notice I get 1 over 2 plus 3, which is 1/5. That tells me, because it didn't make my denominator 0 anymore after I simplified it, that it's a whole at 2 1/5. Then if I look at x equals -3, when I plug -3 in here for x, -3 plus 3 is 0, and we have 1 over 0, which makes my denominator 0, which means that at -3 we have a vertical asymptote. And that's the difference. So let's go ahead and look at the next one. So this one simplifies into 1 over x. My area of concern is x equals 0, because that's what makes my denominator 0. When I plug it into my simplified answer here, it still makes my denominator 0. Therefore, at x equals 0, it's a vertical asymptote. And looking at this last one, so for this last one, I need to factor in my numerator, which is the difference of two squares, so x plus 2 times x minus 2 all over x minus 2. And so when I do that, you notice you have a common factor between your numerator and denominator, which is that x minus 2, so those cancel out, and it simplifies into x plus 2. So if we look at my denominator here, what makes that 0? X is equal to 2, because 2 minus 2 is 0, so that's what we're concerned with. So if I plug that 2 into my simplified answer, 2 plus 2 does not make my denominator 0, it's actually 4, so that tells me that this is a whole at 2, 4. And again, that's because when I plugged it into my simplified answer, it no longer made my denominator 0, and that's why it's considered a whole of my equation. And that's it. So then tomorrow we'll talk about horizontal asymptotes and how they affect our graphs.